So in this video, I will talk about the kinetic energy in rotational motion and the moment of inertia. Suppose you have this system of three particles in rotational motion, and they are rotating around this axis of rotation. This is the point that the axis is coming out, and all these three masses are rotating around this axis with a common angular speed. And the suppose there are rods. These are the rods, rigid rods, which you can ignore the masses that connect every mass to this rotational axis. So these rods are fixed. These rods are just connecting all masses to the rotational axis, the point of rotation, and they are fixed. They're not changing the angle in between them. They're just fixed. And all the system is together rotating around this center of rotation. So these are the masses M1, M2, and M3, and every mass has a distance to the center of rotation, like R1 is the distance of the M1 to the center of rotation, R2 and R3 similarly for M2 and M3. So all these distances are also given. All we want to know is that how do we write down an expression for the kinetic energy of this motion, rotational motion. Since, even its rotation, the objects are moving with some velocities, with some tangential velocities. Let's also call these tangential velocities put over here. This is V1, this is V2, and this is V3. So as the system rotates, all these velocities all the masses first of all will be having a circular trajectory, and every point of this trajectory, their tangential speeds will be tangent to the trajectory, like this one and this one. But we know that the rotation for all of these masses has a common angular velocity. Angular velocity for each of them are the same, but of course these tangential velocities might be different because they have different distances to their center of rotation. And we know also that we can express each of these tangential velocities in terms of the angular speed, angular velocity. And these are like V1 is omega times R1, V2 is omega times R2, and V3 is omega times R3. And these are, I explained, I just made the connection in previous lectures, like in kinematics of rotation. So, in general, these R's might be different, so that tangential speeds will be different. So when you express all the total kinetic energy for the system, it is going to be just 1/2 total of all masses multiplied by with their velocity squares, right? And of course, I for this system is running from 1 to 3 because we have 3 masses. But instead of VI's, we can express these velocities in terms of these omegas, right? Instead of VI, V1, let's say put omega times R1. Instead of V2, we can put omega times R2, etc. So if you do this, you will have this result that sum of all velocities, sum of all masses multiplied by distances to the center of rotation squared. And since omega is common for all of them, we multiply this with omega squared. So, as you see over here, the kinetic energy for this specific rotational system turns out to be 1/2 some quantity multiplied by omega squared, where omega is the angular speed or angular velocity. And that parenthesis expression in the parentheses is all about masses and their distances to the center of rotation, or the rotational axis. So this is called a special name, and we call that, we symbolize as capital I, and this is the moment of inertia of the system. So moment of inertia. Okay. So moment of inertia contains the masses together with the distance squared for each masses to the center of rotation, multiplied by distance squared. And of course, we have, if you have more than one mass in the system, you add them all. So this is we call moment of inertia, and in this case, we can express this kinetic energy of the rotation as this simple form, 1/2 I omega square, which is very similar to, remember, 1/2 mv square for the kinetic energy of a mass which is going with the speed v. Okay, so I mean it's a nice form. So it's only about the kinetic energy of the rotation. And so as you see, it's over here, this moment of inertia like is playing the role of mass, and omega is playing role of the speed, or tangential speed. So when it comes to rotation, there are always these remember, counterparts. X, the linear distance, is counterparted by the angular distance, like v is counterparted by omega, and the linear acceleration is counterparted by alpha, the angular acceleration, etc. Goes like this. So that means eventually m is represented by moment of inertia, right? And but this will keep going on. Later we will also include force and torque, and also the angular momentum. So the kinetic energy over here is similarly has a very similar form in that of the linear kinetic energy expression. So all we have to do is, you don't have to deal with the individual different speeds for the particles. In that case, in this form, you only gotta know what the common rotational speed or angular speed. That's it. But you have to calculate, in that case, this new quantity which we call moment of inertia for your system. And if your system is does consist of point particles which have some distances to the rotational axis, this is the definition. I mean, this is the expression for the moment of inertia. You multiply each mass by distance squared to the center of rotation and add them all. This is how we calculate moment of inertia. It's not a very difficult task to do it. Anyway, the best, I mean, the nice way of representing the kinetic energy of rotation in this form is because we have only one single angular velocity, and it is the same for all the objects, even their tangential speeds are different. Okay, so I mean, of course, not all objects, not all systems of rotational rigid systems composed of the point particles, like in this example. For example, suppose you have a rod like this, which is a distributed mass, which has a distributed mass. It's not a point mass, and it's a rod. Let's say it's a uniform rod. Let's say, yeah, that means every part of every single piece of this rod has the same density. And suppose it has the total length of, let's say, L, and you want to rotate this rod along this axis that just touches its left end. So it will rotate around this axis in this manner. Okay, so in this manner, so its rotation is somewhat going out of the page and going like this around this axis. So it's going like this. Okay, so Uh, First of all, you might want to express, let's say, if it is rotating with some angular speed omega, you want to express these rods kinetic energy. So I mean, you know that it is going to have this form. We already shown here. Although we have shown this expression for the kinetic energy of the rotation for that particular system, this format is true for all systems of rigid body rotation. Okay, so this is also will have this kind of kinetic energy expression. But the thing is, since this rotation of the continuous extension of the object, which is rod, is rotating with a common, so every part of it, every single piece point on the mass on it will rotating with the same angular speed or angular velocity. So it's very obvious that the rotational kinetic energy will have this form. But the thing is, how can we calculate in that case the moment of inertia for that distributed mass along this one dimension? Suppose you take this dimension, this axis to be the axis of r. Okay, so we know that the moment of inertia can be calculated for point masses like this. The best way to approach the problem is maybe just divide this rod into small pieces, which you call small masses. Since infinitesimally they are small, we call them dm's. Okay, differential masses. I mean, let me write this in a clear way. This is dm. Well, we call this dm because it's very small. I mean, you can take this as a point particle. All right. So this is the trick that we have done many times before. So, one thing that we want to know about this particular choice of dm is that what is its distance to the axis of rotation. Let's take this distance to be r. Okay. And obviously for all dm's that are chosen on this extension of the rod, will run from 0 to total length L. Okay, but for that particular dm, it is distance to the r, and dm is the mass of that piece. So we can always take this dm is infinite as it's infinitesimally small, arbitrarily small. We can express the moment of inertia as the sum of all dm's, okay, running through this extension with their distances to the axis of rotation. So obviously, I mean, I'm talking about if you treat these dm's as like point particles, and every dm has a distance ri, let's say, call all these dm's, different dm's as with labels dmi's, and this is going to be square because we have to square it, and sum them all. Okay, sum them all. Well, I is going to be for all of the pieces, but the thing is, you can divide as many small pieces as you want. That means all small pieces might be arbitrarily small. That means this sum you will go to integral, right? And this is the trick we do. So just drop these subscripts and replace this sum by integral, and this is going to be moment of inertia. Okay. Well, we have to take this integral, but the thing is, these dm's should be expressed in terms of distances r's, because r's are changing. But the thing is, these dm's also have some extension in the r direction, right? So we can always write these dm's as density of the rod, which is, let's say, rho, mass density of rod, multiplied by dr's, because every dm has some extension in the r direction, right? We can simply say this. It's no big deal about it. We know because all these dm's are along this extension, so every dm will have some length in the r direction, but these lengths are going to be infinitesimally small or arbitrarily small. then these lengths can be expressed as drs. Okay, but how do we get dm? Since it's a mass extension, it's a one-dimensional extension mass, we have to multiply every dr by the density of the mass density of the rod, so we get dm. So you will be able to just write this down easily when you think about all dm's are extension in the r direction with some length of drs. Okay, but what about this the mass density? Well, mass density, since the rod is uniform, mass density is nothing but total mass divided by the total length. That's it. Okay, this is the density of the mass, total m divided by total. So next is everything is more clear now. So just replace dm inside the integral by this r square m divided by l. Well, m is constant, l is constant, multiplied by dr. And what about the limit of the all these drs? Well, they will run from 0 to total length l, 0 to l. Okay, so we can take this m divided by l ratio simply out of the integral because it's just a constant, and you can just take this integral r squared dr. That's it. Okay, so its integral is very easy. R squared dr is just r cubed divided by 3. So if you put this to l, then you get 1/3 capital M total mass of the rod multiplied by L squared. So this is the moment of inertia for a rod, that the rod is just rotating around one of its endpoint in this manner, okay, with some angular velocity. So in that case, the kinetic energy is just 1/2 multiplied by I, which is 1/3 L squared multiplied by omega squared, whatever the rotational angular speed of the rotation. It's going to be having this last form, whatever the angular velocity is. As long as you know the total mass and total length, you can easily calculate the kinetic energy for that rod. Well, this is just one example of calculation of some regular shaped rigid bodies. Particularly we have just calculated a one-dimensional rod, a standard rod. And of course, there are many different regular shapes like discs, like wheels, cylinders, like spheres, hollow spheres, solid spheres, etc. They're all distributed masses, and they all have different moment of inertia. Well, for that rod, if you just, as I said, rotate the rod from one of its endpoint, what if you have a rod, the same rod, which has length L and mass M and length L, what if you are rotating is around the center, around its geometrical center? You rotate it around the geometrical center with omega, and in that case, what is going to be the moment of inertia? Well, the moment of inertia will change in that case, because in this case, all these distribution of the masses with respect to its rotation changes. I mean, over here, the distribution of the masses extends from 0 to L, but over here from 0 to L over 2 in the right and the minus L over 2 in the left. So at most, the most distant particle will be just having a distance of L over 2 from the center of rotation. Obviously, this rotation will have different moment of inertia, even if the rod is just the same with that one. If you calculate by the same tricks that I use over here, in that case, for this rod, that rod is rotating around its midpoint, the moment of inertia will be 1 divided by 12 L squared. Okay, keep this in mind that not only the moment of inertia is determined by not only the shape and the mass of the object, also the distribution of its masses around the axis of rotation is important. These axes are different in both cases, so you get different moment of inertia. So I will only just give you the moment of inertia of all other regular shaped solid objects, like a wheel. Okay, suppose you have a wheel, all of its mass are on this peripheral circumference. So every part of the mass will have the same distance anyway. Let's say this has as a radius r and a total mass m. The moment of inertia for a wheel or a hollow cylinder, or it can be a hollow cylinder also, is going to be mr square. Well, if it is a disk, you might have a disk that the mass is always all distributed over the area of its surface. Again, suppose it has the same, it has the radius r and the total mass m. In that case, the disk will have the moment of inertia 1/2 m r square. Well, if you just compare that, suppose these two objects, like this is disk and this is the hollow disk or a wheel, and having the same r's, having the same radius, having the same mass, why do you have different moment of inertia? When you just think about it, uh, in the case of wheel, all of the mass are having the same largest distance to the center of rotation. So obviously this should have a larger moment of inertia, because some of the masses approaches to the center of rotation, and they will be having a smaller tangential speeds, which contributes to the total kinetic energy smaller. In that case, totality, you will have a smaller moment of inertia. That's reasonable. Okay, this result is reasonable just by just thinking. Of course, you can easily calculate this. This should be result in this way, 1/2 mr square, and you will see of course, but just by looking at it, it's very obvious that the moment of inertia in the second case, in this disk, is going to be less than this one. Or how much less than is it's up to your calculation anyway. You will see. So suppose you have, next is a solid sphere, a sphere which has mass all over its volume, and let's say it has again total mass m and radius is r. In that case, the moment of inertia for that solid sphere is going to be 2 divided by 5 mr squared. Okay. And for a sphere which is a shell, okay, the all masses are distributed on its shell, and the this region is just hollow. Again, having radius r and total mass m, the moment of inertia is going to be just 2/3 mr squared. So these can be calculated, but I'm not interested in showing these calculations to you. In problems, most of the time you will be given whatever the shape of the object is. These moment of inertias will be given to you. You don't have to memorize them. Okay, so that's it about the kinetic energy of a rotational motion, and how do we associate the moment of inertia for every different type of distributed objects, be it a system of point particles or an object which has a distributed mass.